Yeah, so thank you very much for the invitation. I will talk about a story about that connects quantum phase transition to a CFT, which is, as indicated here, is the cubic CFT, which is based on a series of works over the years. It's actually a kind of a large collaboration with my friends. My collaborators are all listed here. We use a lot of techniques, which includes quantum Monte Carlo simulation, DMRG techniques, exact diagonalization, and quantum field theory techniques. So just to put this story in the big picture, this quantum loop model is related to Z2 spin liquid. It's related to topological phase of matter. It's related to frustrated magnets, which means that well, I'm putting it on the triangular lattice, so it has some frustrations. It's related to the recent experiment of Rydberg blockade, which is a new experimental stage that people use to play with this kind of models. Unfortunately, I'm not an expert on all these topics. I will just explain the roles I played as a field theorist, a conformal field theorist, more precisely. Just one more word is that, I mean, if you are from integrability, on square lattice, the full effect loop model can be mapped to the famous six vortex model. However, we are going to study it on the quantum, we are going to study a quantum model, also on a non-biparty lattice. So the physics would be very different. So I think this is an audience with diverse backgrounds. So I will try to explain the basics. First, start with something with the basics of quantum phase transition. So let's consider the simplest one, which is basically the transverse field Eason model. As you can see here, let's just define it on a square lattice, for example. And I'm introducing nearest neighbor interactions between two spins. X, Y, Z are polymatrices. So I'm talking about Hamiltonian. I'm not talking about the Boltzmann measure. When we talk about finite temperature transitions, we usually talk about the Boltzmann measure. This is a Hamiltonian. And if you have infinite calculational power, you can just diagonalize this Hamiltonian and you got the physics. But this is not easy. So these are therefore the way to do it is to use whatever method you have, like simulation. But let me see that the operator, which is defined by x on each side, sorry, there should be a circle, on each side is an operator that commutes with the Hamiltonian. This is a globally defined Z2 action, and therefore it indicates that the system has a Z2 symmetry. We can try to diagonalize it in some limit. For example, when the transverse field is much less than the coupling, you can neglect the second term. You found that basically your system has two ground state. This should be ground state with plus. One is like all the spins are pointing plus. Another is that all the spins are pointing at the minus direction. But as long as you turn on this coupling, it's not the state is not as like this anymore. So it will have corrections. But still, we know that this is in the symmetry breaking phase where the Z2 symmetry is broken. On the other limit, when H is much larger than the coupling, we can neglect the first term and just to focus on the second. Sorry, there are typos. And the ground state is basically the ground state of a spin pointing along the x direction. And you can calculate the expectation value of your spin, which is 0. Okay. So from this, you see, okay, we are dealing with the system with symmetry breaking. So as you change the transverse field H, you will start to see the symmetry breaking patterns. So one can actually start this at finite temperature. And the phase diagram you are getting would be something like this. You have a parameter of Hamiltonian at 0 temperature. You have a parameter of Hamiltonian that you can tune. so that it goes from a disordered phase into an ordered phase, okay? But then you can change the temperature. You find that there is a line of fixed point, line of phase transition point, which is again given by symmetry breaking. But this is given by, well, this would be a 3D is a model, and on this line, it would be 2D is a model. Why is it a line? Because we know that, well, Anzag solved the 2D is a model for us. We know that the 2D is a model has just one relevant operator, which does not break the Z2 symmetry. So therefore, it should be the codimensional one. It should correspond to a codimensional one plane in your phase diagram. I mean, we are in 2D, so codimensional one is a line. So therefore, this whole line is the 2D is a model. So in some sense, if you are sitting here, you turn on the epsilon operator, which is relevant, that brings you away, that drives you away from this CFT, and you are in the ordered phase, or disordered, or ordered phase. On the other hand, if you turn on other operator, like epsilon primes, these irrelevant ones, what it does for you is just let you like change along these lines, and you don't really change the physics. In the deep infrared, you are still getting the Eaton physics. So this is the basics of quantum phase transition. But how do we understand this in fixed-feature language? Landau told us that, okay, the first thing you should consider is the spontaneous symmetry break-in. Consider free action, free energy, written in this form, which the Z2 symmetry is given by phi equal to minus phi. And when mass is positive, the system is in the symmetric phase. When the mass is negative, the system in the symmetry break-in phase. It's like before. But how about finite temperature? We will have to include a kinetic term, which is a kinetic term that suppress fluctuations, right? So fluctuations cause large, has non-vanishing value for this action, so it's suppressed. So we can do this in lambda phi 4, for example. And to understand finite temperature, well, what I'm explaining here is basically this line as you cross at zero temperature. This derivative I'm writing here has both space and time. This fluctuation is given by quantum fluctuation. But you can go to finite temperature when you are looking at large scale physics, long distance physics. You perform a closed Klein reduction along the temporal circle. Well, I call it closed Klein, but really it's just a finite temperature expansion in terms of Mosvara frequency. So let's do a 4D system first. You can integrate along this temporal circle. And this mode has both the zero mode and the massive mode. So what you are getting is an interaction theory between massless ones. Okay, sorry, I turned m equal to 0. So it's a free theory scalar, and it's a bunch of massive scalars whose mass is given by the Mosvara frequency. So this lambda introduces interactions between them. So there is an interaction between the massless and the massive ones. Well, there's a self-interaction between for the massless ones. You can just do a one loop calculation. This is taken from one paper by Zohar called conformal order. The loops, the massive modes that propagating along the loops would renormalize your zero mode. Basically, you are performing a one loop calculation like this. This is the mass. This is the space momentum. This integral is not it's divergent, but you can regularize it using gamma functions or whatever. And then you get a summation of infinite of integers, and this you can regularize it using Z function regularization. In the end, you find, okay, we get a term which is proportional to beta. Beta is 1 over t, which is inverse mass. So this is your thermal mass. Now, when does phase transition happen? Phase transition happens when total mass is 0, when the potential change from W shape to a U or just one minimum. So therefore, well, near the quantum critical point, you can basically take this mass to be proportional to the h minus h bar, which is how far you are away from the fixed point. It's some physical parameters. We are doing a Taylor expansion around the critical point. We need total mass to be equal to 0, we have the one given by the changing of physical parameter. We have another piece given by the thermal fractions. They have to be equal to 0. Then you get some Tc equal to h minus h bar to 1/2. This is the 4D calculation. If you go beyond mean field theory approximation, go beyond 4D, you can do formalize epsilon. This lambda would be the CFT lambda, the critical coupling at the CFT point. And your mass, you need something relation. Instead of getting a 1/2, which is the mean field theory value, you should get a nu, which is your critical exponents, one of the thermal critical exponents. So when we draw the phase diagram for quantum phase transition, we always draw something like this. But why is it like this? I mean, I always was curious. But then the way to answer, why is it not like asymptotically approaching 0? Why is it not going to the left? But this is basically a calculation. This is the power law behavior of your phase transition line. So this is determined by thermal calculation, thermal field theory calculation. Okay. That is basically how to understand the phase diagram. So today's talk is about phase diagram that is the phase diagram of fully packed quantum loop model on triangular lattice. The phase diagram we are going to look at is the phase diagram of that model, which looks like this. V is some parameter like the transverse field for easy model. There's temperature, but you can see there is a line of fixed point, which kind of looks like a power law because it's 0 temperature, therefore it's very hard to actually simulate. But it looks like this. So, but before that, I want to spend some time to explain how to get a field theory from the lattice, okay? So let's imagine, instead of considering the loop model, let's imagine considering some model which is much more simpler. We have a two-dimensional plane, which is the surface of some material, let's see. We have some atoms, let's see, red atom and blue atom. I won't tell you what it is. It's absorbed and onto the surface. And this is actually an actual experiment that actually Daisy in the 70s, they do a lot of like this, this kind of experiment. But at high temperature, the average density of red or blue atoms at a specific site is 1/2. Let's just see there's an equal distribution of red and blue. As you lower the temperature, you would find the atoms start to form some structure, like red, blue originating structure. So then the probability of finding a red atom is given by 1/2, then plus a -1 to the x plus y. X is the lattice indexing lattice, y is the index for the y direction. So the order parameter is basically the coefficient in front of this for this phase transition. This is a toy model, but well, you can engineer some interactions among hardcore bosons to species and make them do this kind of thing. Then this coefficient is order parameter. The point is that the space group on a lattice, we have a lot of symmetries. There's a space group is given by translation, by rotation, but this discrete translation. This space group are unfeasibly represented on the order parameter. What do I mean by that? It means, let's see, translation along x direction, which is basically x goes to x minus 1, then you just pick a minus sign, right? So because I just take x, go to x plus 1, and I pick a minus sign. This order parameter change sign as I do an x direction translation. On the other hand, translation by two sides is not changing anything. It acts trivially on our order parameter. This is why we see it's an unfaithful representation, okay? This is a mathematical word, but really it means that in the Brillouin zone is a momentum space on the dual lattice. This -1 to the x plus y can be written as exponential pi x plus I pi y. So your order parameter is that momentum pi point. Okay, this is the special point in your Brillouin zone. So rotation, as I if you remember in periodic boundary condition, rotation Brane zone is a torus. So if you rotate this pi to here, it's equal to the original point. So rotation also acts trivially. Okay, so this is basically the Landau theory for structure phase transition or for this kind of absorbed all atoms on the surface. So the order parameter is some specific point in the Brane zone. It's a specific representation of the space group, but it's an unfaithful representation. The space groups, some of the space group elements acts trivially on this order parameter. Okay, I hope this is clear. Therefore, I mean, to figure out the order parameter is basically to figure out which representation you are talking about. It's driving your phase transition. The fully packed quantum loop model, I put self-avoiding here, but it's not really important. The quantum loop model on triangular lattice is defined again as a Hamiltonian, very similar to the transverse field is a model Hamiltonian. The Hilbert space is given by the loop configurations. All these possible loop configurations, that's the Hilbert space. The condition is that there are two dimers per site. That's why it's a loop. It's all possible loop configurations is at well, yeah. There are two terms. One term is a potential-like term. So if you see a parallel dimers, it gives you some energy. If you see horizontal parallels, it gives some energy. Another is like the flip, the signs. You can also similarly try to understand what are the phases. If you are, V is very large, when it acts on this term, it's zero because there's no parallel dimers, so it's zero. So you are in this state. On the other hand, this term vanishes on this. So therefore, on the far left, you get another phase. So when you have a loop, there's a way to map it to so-called Y-zone configurations. The thing is also very easy. You pick a plus sign here. Whenever you cross the loop, you put a minus sign there. Okay, and this is of course, there is a convention about whether you are putting plus or minus here. So this is a convention. It's a gauge. So the order parameter we are having is something very similar to what I explained for the square lattice absorbed items there. You don't really need to know the details. What I'm trying to see is just that this is an order parameter. The order parameter is a special point in the Brane zone, and the space groups plus this Z2 gauge, the X non-trivially on these order parameters. But the X, they form a smaller group, which is a group that is faithfully represented on this order parameter. So this is how you derive the effective action for this order parameter. Okay, this is what I was trying to explain. So these special modes are picked so that there are some special points in the Brane zone. We are on the triangular lattice, so the Brane zone looks like this. It's not important. But the point is that the space group acts on this order parameter by these generators. Tx is the translation, Ty is y direction translation, inversion is bound inversion, R6 is the six-fold rotation, Z2 is the gauge we were talking about, the freedom in picking the gauge. We can flip all the y-zones, we don't change. My M is some mirror reflection along some plane, I think. These were derived in these papers. But what if you look at this group, you notice this is a cubic group. In other words, my effective action looks like this. Is the three scalars, and there's a mass term. Okay, I forgot another term, which is phi1 plus phi1 square plus phi2 square plus phi3 square bracket square, which is the ON preserving one, O3 preserving one. This is the one that breaks ON to the cubic group. What is the cubic group? The cubic group does this. It's given by Sn rest product of Z2 to the power of n. Z2 is flipping each copy. You can flip phi one, change the sign of phi one. It doesn't do it doesn't break the symmetry. You can flip the second copy. It doesn't break the symmetry. You can flip the third copy. It doesn't break the symmetry. But there's another SM piece, which is the permutation of all three copies. Okay, so this is a maximal subgroup of ON, which is a popular model in the 70s. Well, people considered lambda 5. After Wilson Fisher, people considered ON, and the next thing you consider is this. This is the CFT. So all I was trying to explaining to you, all these earlier discussions, is basically to tell you that there is a lattice origin for this symmetry, and we are getting a cubic effective action on the theory. Now we can put on our head of a field theorists and analyze this CFT, this system. The first thing you do is mean field theory. You find that the mean fields, there are two phases. Well, if you truncate it to 5, 4, there are two phases. One phase is that when this guy has a positive coefficient, phi 1 equal to phi 2 equal to phi 3 equal to some constant. So I'm drawing it on a cube. Horizontal, this axis is phi 1, this axis, the axis going into the plane is phi 2, the axis pointing up is phi 3. So my vacuum has equal value for phi 1 and phi 2 and phi 3. So it lives on the corner of a cube. Okay. The cubic symmetry I mentioned is basically the symmetry of a three-dimensional cube. It's all the symmetries that does not change a three-dimensional cube. So my vacuum is located at the corner of the cube. So this is, I mean, it's nothing fancy. You start with this potential, you minimize it, you look at where the vacuum is, right? So nothing fancy. Another one is when this V4 is less than 0, the vacuum is located at the fifth center. For example, this one means phi 1 equal to some value, phi 2 equal to 0, phi 3 equal to 0. So this is one of the vacuum. So it's conventional to call this guy corner cubic. It's conventional to call this guy fifth centered cubic. Okay. It was already noticed in a very early paper by Aharoni, that you can basically generate this to n copies because the cubic group can be generalized to n copies. And there's the RG flow analysis using perturbatively informalized ipsum. There exists an NC. When n is bigger than NC, your RG flow looks like this. The ON CFT is unstable. The actual stable CFT is the cubic one, the generalized cubic CFT. When you do n less than NC, on the other hand, sorry, I should put ON here, but what happening here is that the ON one is not stable. It's not stable. It is stable, but the cubic is not stable. So there's a change of stability. What are the actual calculations here? You calculate the beta function. You in format ipsum. You find the fixed point. You then calculate the Jacobian, another derivative with respect to the coupling. This forms a Jacobian. And then you look at the stability, the eigenvalues of this Jacobian, either at the cubic fixed point or at the ON fixed point. You look at whether there's a relevant direction or not. You just find that there's an NC where these ON and cubic, they shift their stability. Okay, this is a very simple stuff, traditional calculation we do for CFT, just like the easing. Remember, in the Wilson-Fisher fixed point, you find at the coupling, if you do another derivative, partial beta, partial g gives you the anomalous dimension for the phi-4 operator. This is the calculation of calculating the anomalous dimension of phi-4 operator. But since we have two couplings, we have to calculate the coupling and find the eigenvalue. Okay, this is nothing fancy. So therefore, determine this NC is the same. So it's an important thing. And this is a long-standing question. Actually, there were some early bootstrap attempts by me and Ningsu, by Sturgill, and by Andy and Stefanos. These were not as as successful as the OM. We didn't identify the CFT. It's actually a quite hard numerical bootstrap problem. But the stability thing, oh, okay. Also, Martin Hagemarsh, he used improved lattice models to study this using Monte Carlo simulation and did a lot of amazing work. The dust was completely settled by the O3 vector model bootstrap. Okay, this was by all these people you know. And this is by analyzing the scaling dimension of the symmetric traceless rank 4 tensor. So this one, this operator, if you make it traceless, it's in the symmetric traceless representation of the O3. So you are sitting at the O3 CFT, you look at whether that operator is relevant or not. If it's relevant, you are in this picture. If it's irrelevant, you are in this picture. So by bootstrapping the O3 and look at the scaling dimension of that operator, you can tell which picture we have. Okay, this is what people did, and the bootstrap is the proof, as we were talking about. It proved there's an upper bound on T4. I think it's below 3, basically. Okay, the scaling dimension is below 3, so it's a relevant direction. This is a very solid proof that we are in this picture. Okay, and I think from Monte Carlo or from extreme functional, it's probably this value, something like that. As you can see, it's very slightly relevant. It's very small. It's very close to 3. So I forgot to put the arXiv number there. There are 2 CFTs are very close. You can put conformal perturbation theory to calculate data for the infrared one. It's called large Q and cubic CFT from perturbation, something like that. It's another paper by me and Insu. So we are in this picture. So what does this tell us? So it tells us, in fact, the phase transition from the disordered phase to the ordered phase is a phase transition from the disordered phase to the corner cubic. Remember, the mean field theory we learned, I mean, if this guy is bigger than 0, we are here. So the phase transition has to go from disordered to the corner cubic. This guy is not there. So this is basically the important lesson we learned from this bootstrap result. And this phase diagram we obtained, in fact, this would be the face-centered cubic phase. This is the corner cubic phase. So as I mentioned, because of the bootstrap and renormalization group and mean field theory analysis, the disorder, the second order phase transition from here has to go into the into the corner cubic first, and then maybe it will go to the face-centered cubic. So this is a very small region of a new phase of this model that is predicted by bootstrap and by RGFlow combined together. And we used basically Monte Carlo simulation and all the other approach to find this. As you can see, this is quite small. Also, what I'm demonstrating in this small figure is that the fine temperature transition line is following a power law, and the power law is given by the nu of O3. Why am I using the O3 value? Is because I don't know the value for, for cubic, but they are very close. So I'm using the O3 value. Also, you can see this data is not perfect. I mean, it's very hard to do simulation at fine temperature. So therefore, it's quite hard. But it kind of looks like this. So I mean, there were like previous studies of this model using simulation, which they also started this system, but they didn't find this phase. This is the phase that was missing before us. And bootstrap is, since bootstrap is powerful, we know it must be there, and we found it.
Sorry,
Also,
Junchen,
go ahead.
ask a question. Yeah.
Yeah.
So why don't you know the new? Can't you do conformal perturbation theory to get the new in the cubic thing? Is there some OPE coefficient that you're missing? Or
We can. I just didn't do it. This case, I think you need no. Let me see. Yeah, you can. I think you can. I just
Oh,
didn't. Yeah,
okay.
it's
But
it's
it's
the
going
first
to make a
order.
very small
Yeah, it's
difference.
the first order correction. Also, I mean, our data, as you can see, I draw a power law here, but I'm cheating because the data is not looking good. So I think the O3 one is good enough. So yeah.
Okay,
I
fair enough.
I I think this is second order in conformal perturbation.
Why?
So first order,
Why?
oh, that's what you told me. The correction on T and W are first order, but for for this is for epsilon, second order.
Okay. How?
Oh, because there's OP coefficient that vanishes at first order. Okay,
Oh,
maybe.
okay.
Probably.
We don't need to think about it. But
Therefore the correction will be very small. It would be
Yes,
10 to minus 4.
okay.
thanks.
Okay, I need to think about it. I'm forgetting conformal perturbation theory details. So,
No, but
uh,
if this is an epsilon operator and you're deforming, right? If it's not charged under the cubic
yeah.
subgroup and you're deforming by something that
Ah,
is,
I see. Yes, indeed. So let me basically see what this discussion is about. So the T4 operator is charged under O3, so it's a non-trivial representation of O3. So leading order conformal perturbation, we need an OP coefficient which is epsilon, and T4. This guy vanished because of O3 symmetry. So we don't have corrections at leading order. The corrections start at second subleading order. We need a 4-point function of T4, 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 which you can obtain if you really care. But again, as I said, as we mentioned, I mean, T4 is already quite small, so the second order corrections are even smaller. So it's a really, really small number. I think for epsilon and for eta, you can use this. Okay, that's the story about conformal perturbation. So from in Monte Carlo simulation, we use a histogram to look at what the system does. So this is a histogram as you are moving along this direction. Okay, so initially it's in the disordered phase. This is the top-down view of the phi plane, and it starts to develop corners at corners, but then at some intermediate value, it became abruptly into the fifth-centered cube. Okay. So I mean, since this is a different audience, let me just see how do we see scaling symmetry in our in Monte Carlo simulation. So you basically measure the value of your order parameter at different coupling, different weight coupling, and then you should use your critical exponent to try to rescale this data. The first rescale is you rescale this phi by the lattice size with respect to beta over nu. These are the two exponents determined by delta phi and delta epsilon. Okay, and you find that they meet at a single point. This would be a signature of second order phase transition. If you don't have this crossing, usually it's first order. And then after that, you can again rescale how far you are away from the critical point. Because we have power law, everything is power law, we can rescale how far you are away from the critical point by the size of the lattice. And then you can see that the data overlap. This is a sign of scaling symmetry. And when you try to do this rescaling, you need to use critical exponents. And again, we use the O3 critical exponents, and you can see the data already match quite nicely. So, I mean, I have to see that this is necessary because even though I argued for you that the order parameters are the phi's I wrote down, I argued for you that this is the future description. The lattice weird things can happen. For example, if you have a lattice system, you are pretty sure that it's given by some continuum mean field theory model. As you change the parameter, maybe some another state which goes down. So instead of being in the CFT state, you could suddenly jump from the CFT state to some other state, which is the first order phase transition from CFT to some other stuff. All these things can happen. So you have to do a simulation to actually confirm that this is what you are getting. So what I'm showing here is that indeed the simulation suggests that we are getting what we are expecting. So this is the CFT, this is the cubic CFT, and there is a new phase. And okay, I think I mentioned this. This is very small. This phase is very small. That's also because the two CFT are very close to each other. The disorderness is the anisotropy is very small, so this phase would be very small. Okay, so now the most recent paper we did is about the sum of phase transition from all these phases, either from here to here and from here to here. Okay. So we did a analysis very similar to what we are doing here, and we showed that the transition from this side, from the phase-centered cubic to disorder, is given by the Potts model, three-state Potts model. We have very strong evidence for that, numerical evidence. Why is that the case? As I told you, we are in the Z2 gauged theory. We have the freedom of picking whether it's positive or negative. So this is the gauge case. So for example, on the corner cubic, you have 8 states, but it's not really 8 states. It's like 4 states instead. So if you mode out the Z2 symmetry, you find that they form a triangle, they form a tetrahedron. Okay. If you mode out it for the phase center, you find the triangle. So this is where the S4 symmetry acts naturally on tetrahedron, and S3 symmetry acts naturally on the triangle. So we have a 3-state respecting the S3 symmetry. We increase the temperature, and the transition is from 3-state to disorder. So we should expect such a transition. So this is what's happening. You turn on temperature, the thermal transition is a computation between energy and entropy. The free energy, ground state energy and entropy are competing each other. So you are either getting the symmetry break-in phase or the non-break-in phase. Okay. So, but this is not really the whole story yet, because you can, near the quantum critical point, you can try to understand using another language, which is what we introduced at the beginning of the talk, which is putting a CFT at finite temperature. So as I convinced you, we have a cubic CFT, and we could put it at finite temperature, and we should, again, expand it into Masbara frequency. But now this mode can take half integer because we are Z2 gauged. So we are allowed to take a minus sign as you perturb it. In fact, nothing changed. I mean, if you do it for the easy model, what you are getting is that still a positive mass. It's just the size of the mass is changing. Okay, it's changing to be half the size. So we need a so I mean, after you perform these calculations, this closed Claude reduction, so what you are getting is a 2D system with the cubic symmetry. And what is that cubic symmetry? What is that CFT? We don't know, in fact, but we have some candidate. The simplest candidate is the so-called decoupled Ising model. Okay. What is decoupled Ising model? Decoupled Ising model is basically 3 copies of Ising model. Okay, this is a CFT. Well, I mean, each copy is a CFT, so it's a CFT. It has more stress energy tensor, but it's a CFT. So why am I saying it has cubic symmetry? Is because each copy has a Z2 symmetry, There's a permutation among the three of them, and that's the cubic symmetry. But also the CFT has a marginal operator. Why is it marginal? It's because I want to find all the operators that preserve this symmetry. The simplest thing you can write down is epsilon I, epsilon g, I not equal to g, summation over all the possible pairs. Okay, so our system, I mean, in quantum field theory, we know something called what can be generated will be generated. So we have to take into account the effect of this operator as you deform away from the CFT, from the critical point. And we have to understand this RG flow with this one involved. But this is, again, something within the framework of conformal perturbation theory. Because the beta function for k, which is the coupling in front of this guy, can be calculated using conformal perturbation theory. It's starting with chi-square order. Why does it start with chi-square order? Because the k equal to 0 order vanish because it's a fixed point. K equal to 0 is a fixed point. K to the first order vanish because this operator is marginal. It's precisely equal to 2. I forgot to mention that this guy equal to 1, right? This dimension equal to 1, so 2 copies of them. Because we are in the decoupled theory, so it won't renormalize, and therefore this system is equal to, yeah, it's basically 1. Okay, so people did it in the early days, but really this guy depends on the OP coefficients epsilon. This is the conformal perturbation to calculate the beta function. So it depends on these OP coefficients, but there are also some group theory parameters because you are doing this symmetry. You have to do this account. So the RG flow is like this. So on one side, it's moving, it's a stable direction. On the other side, it's unstable. Remember, our beta function is t square, right? So on this side, it runs to the right. On the left-hand side, it runs to the left. So this is a sign of the merging of two fixed points, precisely when they merge. For example, if you take n copies of coupled minimum models slightly away, Ethan is 4-3, but you take it slightly away from that, along some line, you would find two fixed points. One is given by the free series, another is given by the interaction series. You can just do the perturbation to find it. And as you take epsilon to equal to 0, you find that they merge, and you have this kind of seemingly weird RG structure, because one direction is stable and the other is not stable. So you can do a calculation to see that k bigger than 0 favors the face-centered cubic theory, which is unstable, and k less than 0 favors the corner cubic. What do I mean by that? This is essentially phi square. So you can pick the face cubic, which is like phi 1, phi 2, phi 3, non-zero. You plug in this, and you look at whether this guy has a higher energy of the other. The face center has a higher energy. You can basically compare this. And from this, you know that k bigger than 0 favors the face center. So therefore, corner cubic is the stable one. Okay. But as we already discussed, the VP, this guy, the transition from here to here is in the corner cubic phase. So therefore, it is in the stable direction. Okay. So at least near the quantum critical point, we can basically view this as well, I think it should be in the cubic, in the decoupled Eaton universally class. Of course, this is a conjecture. As I said, weird things can happen on the lattice. So it's a conjecture. It remains as a conjecture until now. We haven't been able to prove what it is. So let me give you a little bit more detail. You hear people talking about fractionalization when you do quantum matter physics. So this is in some sense kind of like fractionalization. So starting from the phi, which is not gauge invariant, but you can use them to form bilinear type of operators. For example, this one is like phi1, phi2, phi2, phi3, phi3, phi1. This is the irreducible representation of the cubic group. It has 3 dimensions. Also, similarly, you can form another bilinear, which is phi1 squared minus phi2 squared, phi2 squared minus phi3 squared. The third one is like phi1 squared minus phi3 squared, but it's expressible in the other one. So this is another irreducible representation. The third one is basically the singlet. Okay. This is a 2-dimensional representation. This is 3-dimensional representation. This is what F4 acts on it. This is what S3 acts on it. Because Sn has an n-1 dimensional irreducible representation. This is because a hypertetrahedron with n vertices can be embedded into an Rn-1 Euclidean space. Okay. So the question is whether phi is free or not. Near the quantum critical point, we know it should be free. So that's why we were using this field theory language with lambda phi 4. Away from the fixed point, it is possible that the actual order parameter is these composite ones, not the separated ones. In fact, this is what we observe. When you go from the lattice nematic, the face-centered cubic, to the disorder, you can measure the eta critical scaling relation for the dimers, which is the loops, loop degree of freedom, which in this case corresponds to bilinears, and the Wisons, which is the phi itself. You measure its change as you go through some of its transition, and you try to rescale it using the critical exponents for 3-state pulse model. This is a measurement using dimers. This is a measurement using phis. And you find that they agree with each other. What does this mean? This means phi is not independent. It's not free. It's not independent. So they are the same thing. So the dynamics does not allow phi to propagate freely. In other words, fractionalization did not happen. So yeah, have different critical. But on the other hand, if we go from here to here, we find that the dimers and the Wisons have different critical exponents. You don't have such a beautiful match between these two measurements. So, but this is
sorry, Junchen, just one quick question. So
sure.
Fractionalization, just for clarification, you would have 2 different plots here. Is that what?
Yes, that would be basically what yeah, that would be the case.
Okay.
So fractionalization usually means, I mean, in quantum transition 2 plus 1D, you can find some O2 model, and you could actually, if you look at the O2 XY model phase diagram, you don't find much. But if you do some more sophisticated things, you can find some Higgs-like phase transition, which means that the O2 order parameter fractionalized into some gauge and non-gauge invariant degree of freedom. So here it's quite similar. So you can write an action for pulse model, which we know how to write, which is like a term with cubic interaction. But as you go towards the quantum critical point, you find that one object fractionalized into phis. That's the language we are using. That's why. So they would be different operators in your CFT. They would have different exponents. That's my very naive understanding of fractionalization. So they are not the same. But I should emphasize, basically, this simulation is very hard. First, temperature is low. We don't know. Well, it's hard to do the simulation. Second, there's logarithmic correction. As I told you, there's a marginal operator here, right? So marginal operator always leads to logarithmic corrections. Actually, you can use conformal perturbation to calculate logarithm correction stuff. I think, I mean, in the early days, when people first started to do critical exponents, they measure critical exponents first, but then they started to look at more exotic situations. One typical situation that you see is the Bayesian model in 4D, for example, right? Because it's a free series. Free series, you have lambda 5,4. The 5,4 is marginal, so this is the marginal operator. It will affect your RG flow, making it harder and harder to approach the fixed point as you do this kind of things. This is similar. We have a marginal operator that looks like this. It has logarithmic correction. So we are not sure. There are finite size corrections. Also, another possibility is that our data are contaminated because we are very close to the quantum critical point. If you, in statistical physics, we sometimes study critical theory, but we also study tri-critical theory, multi-critical theory. But when you are sitting at the critical theory and you move slightly away from the tri-critical, you sit at the multi-critical, you move along the line of critical, you have some crossover behavior of critical exponents. This is very similar. So you have a 2+1D quantum transition. You are moving slightly away from it. So there should be a crossover behavior, which is affecting your measurement of critical exponents. So these are all the crazy things that happens. Therefore, even though we have a beautiful theory of conformal perturbation, we don't know what is really happening. So that's a thing. Also, I want to see that the loop model has very large unit cells. So it has quite large, which I didn't really mention it to you, but this phase has very large unit cells, which is again why it's harder to do the simulation. Okay, that's probably all I want to mention. So we still, let me just wrap it up by saying that I'm personally very interested in the space of, say, four-dimensional CFTs. You have a beta function. We consider the most generic one. You have a beta function. This is kind of like the top-down approach of classifying critical phenomena. So you start from some perturbative calculation, you try to classify all possibilities. I mean, in the early days, people had a lot of work with 1 copy, 2 copy, 3 copy, 4 copy, 5 copy. We did it recently with Slava. And you can do some numerical check. Sorry, I again will forget to put Andy Sturgill's nice paper there. Yes, so this would be a classification of critical phenomenons. It appears everywhere. It appears in statistical physical models. It appears in quantum physics transition models. So it's a nice story, and we probably can push this direction. What I was telling you is that I have a gauge theory. I have a gauge theory on with Z2 gauge on the lattice. So what's here is actually the projective representation of the wallpaper group. I told you what is space group, which is in 3D. In 2D, it reduced to wallpaper group. But I have a gauge background, so it is a projective representation. So in the case of structural transition, when there's no projective representation, the actual representations, actually mathematicians worked really, really hard in the early days. They classified all the representations of the space group. Space group there are 230 something, I forgot the number, space groups. They did the classification of their representations. They wrote down the Landau action from these representations, and they analyzed all the possible phase transitions you can have. So there's a list, there's a table. Now, that table is basically what CFT you can get from this type of transition. So if we perform hardcore mathematical classification of projective representations, maybe this is something to do. It's a bit hard, but yeah. So I mentioned there is a fifth corner cubic, there's a fifth center cubic, but in fact there's another one which is called the bond center cubic. This is harder to find. We don't know where it is in our fifth diagram. Maybe introduces some extra extra interactions, you can find it. This is some question. Also, I think I said the theory is quite nice, but we didn't consider Polycode loops. By Polycode loops, I mean the two Wilson line along the temporal circle. So I don't know whether this would change the dynamics or not. So I actually don't know how to study this kind of objects, which is a pity. But also I think maybe a lot of people here are interested in bootstrap. This kind of setup with temperature, but with defect along the temporal line, it's something that we can calculate maybe perturbatively. We can do some kinematics and stuff like that are probably nice. I talked about the dimer model. I talked about the loop model, which is 2 dimer per side constraint. You can do 1 dimer per side, which is actually the first spin liquid phase that people discovered even on the lattice. Now there are experimental playgrounds that people can do this. But there's another one which is 3 dimer per side. It's something you can think about. And in the dimer case, the CFT is actually the O4 CFT. I told you in the loop case, the CFT is the cubic CFT. And the question is in the 3 dimer per side, which is CFT it is. I don't know yet. So that's it. Thank you very much.
Yeah, we thank you, Junchen, a lot for this beautiful talk. And maybe we can stop the recording. And if there are questions, maybe it's time for questions.